Hello and welcome to oh goodness, hang on one second. There we go. Welcome to our first live office hours of the COVID-19 season. I'm just checking on our stream health real quick before we dive in and get started. All right, it looks like we have one. Oh, we had one concurrent viewer. Now they're gone. Like I said, I don't know whether or not this time is good for anyone to tune in live, which is why we've been taking requests through email. So with that in mind, we will be here each week at 1 o'clock. So if you want to get in on the office hours situation, we're going to be here every Friday at 1 p.m. Every Friday at 1. If you can't tune in live, but you still have questions that you want to get answered, we are taking email submissions, or I am taking email submissions. That way, if you cannot tune in and watch with us, you can always dial it up later on the channel. Watch the video to see the problem that you were struggling with worked out step by step. Now, if you were doing email submissions, I would ask two things. First, that your subject line, that your subject line say Chem 400 office hours or hour. As you can imagine, our inboxes, the faculty's inboxes, are all inundated these days with daily COVID updates that we are still experiencing a global pandemic. As a result, though, it's very hard to kind of sift through the emails, and I'm getting, so far I haven't missed any student emails, but I'm paranoid about your inquiries getting buried under the seemingly ceaseless updates. So if you put Chem 400 office hour in the subject line, I'll be able to search that, and all of your questions will be able to be answered. In addition, if you could include a picture of the problem. This does not need to be a high resolution scan. It can just be a photo with your phone. But that way, this will simplify things for me, because the email submissions that I've received so far, I have a photo of every problem. They're sitting here on a monitor, so I can see them, access them swiftly, problem to problem, without having to turn pages, find them in the textbook, etc. So if you could do these two things, it would definitely streamline the process, make sure I don't miss it, and hopefully make these office hours a little more fluid. That being said, let's go ahead and dive in to our first question. So the first question we had is coming to us from. Excuse me. Don't mind the sci-fi noises. Those are just my Android overlords vocalizing their concerns. The first problem we have comes to us from Chapter 6. It's example 6.3 from the textbook. And here is the problem. A 32.5 gram aluminum cube is initially heated at T1 45.8 degrees Celsius. It is submerged into, 105.3 grams of water, whose initial temperature is 15.4 degrees Celsius. And then we're asked, what is the final temperature once thermal equilibrium is reached? All right, so here they give us the mass of aluminum, the initial temperature of aluminum, the mass of water, initial temperature of water, and they're asking us to find the final temperature. Now, true to form, the textbook does not include the specific heat of water or aluminum. We have to look both of these up. I know water off the top of my head, but let me look up the specific heat of aluminum. Alrighty. Oh, that's not helpful. Aluminum. So water has a specific heat of 4.184 joules per gram degrees C. Aluminum has a specific heat of 0.907 joules per gram degrees C. All right. Now you'll notice that in this problem they ask what is the final temperature of both substances. All right. And that is because when you reach thermal equilibrium, the temperature of the water and the temperature of aluminum are going to be equivalent. They're going to be the same. All right. Now, to solve this problem, we have a situation where aluminum is losing energy, right? It starts at a higher temperature than water. You can see it's at 45.8, and water is at a cooler temperature. So aluminum's losing energy, water's gaining energy. This is a situation where we're going to need to write out the heat. We know the heat that water is gaining is the same quantity of heat that aluminum is losing. The problem is they have opposite signs, because if water's gaining energy, it's that quantity of energy will be positive. If aluminum is losing energy, that quantity of energy will be negative. So if we are going to write these two as being equal to each other, we need to multiply one side of this equation by -1. Now that we have this expression, all right, we can substitute, because we know the thermal energy transferred, Q, is equal to mass times the specific heat times the change in temperature. So we can substitute into this expression, that the mass of water times the specific heat of water times the change in temperature of water is equal to the mass of aluminum times, times the specific heat of aluminum times the change in temperature of aluminum. Now, based on our given information, you'll notice that we have the mass of water and the specific heat of water. We also have the mass of aluminum and the specific heat of aluminum, but we do not have the temperature of water or the temperature of aluminum. If we substitute in the equation we know for change in temperature, which is final temperature minus initial temperature, to this situation, that gives us mass of H2O times specific heat of H2O. Now I'm substituting in the final temperature of water minus the initial temperature of water. Oops. All right, I've already seen my first mistake. Is equal to, I forgot, I'm going to highlight it here. This negative sign, so this needs to be negative over here, is equal to negative mass of aluminum times specific heat of aluminum times the final temperature of aluminum minus the initial temperature of aluminum. All right. Oh, we have our first question. In the textbook, it says specific heat of aluminum is 9.03. So will this affect the answer significantly? You know what? So the question is, in our textbook, the specific heat of aluminum isn't 0.907, it's 0.903. Let's just roll with what the textbook has. It might have a subtle effect, but let's just roll with this to be consistent. All right, 0.903. Okay, so we just substituted in, getting back to the step of the problem that we're in, we just substituted in the equation for change in temperature, which is final minus initial, into this equation. And you'll notice that now we have the mass of water, the specific heat of water, and we know the initial temperature of water. We also have mass of aluminum, specific heat of aluminum. We also know the initial temperature of aluminum. This leaves only one variable in our equation. Well, technically two variables, right? We have the final temperature of water and final temperature of aluminum. However, because we are dealing with a thermal equilibrium, we know that the final temperature of water is equal to the final temperature of aluminum. Therefore, we only have one variable, and when you have one variable in algebra, you only need one equation to solve it. So we have enough information to solve this problem. It's just going to take a lot of algebra. All right, and so I'm going to move to the next slide, and we will start algebraically deconstructing this situation. So first, I'm going to rewrite my equation. I'm going to rewrite my equation here. I have my mass of water times specific heat of water times final temperature of water minus initial temperature of water is equal to -1 times mass of aluminum times specific heat of aluminum times my final temperature of aluminum minus my initial temperature of aluminum. Now, there's one of two ways to do this problem. You could plug in all the values that you know and then do algebra to solve, or you could leave everything as a variable. Or you could do a bit of both. I am going to do just a little bit of both here. Oops. All right, so We, remember, need to isolate our final temperature on one side of this equation. So to do that, I'm going to start by dividing both sides of this equation by -1 times the mass of aluminum times the specific heat of aluminum. All right. Mass and specific heat of aluminum cancels off of one side. This gives us mass of water times the specific heat of water over -1 times the mass of aluminum times the specific heat of aluminum times final temperature of H2O minus initial temperature of H2O is equal to the final temperature of aluminum minus the initial temperature of aluminum. Now, for my next move, I'm going to distribute this factor into this parentheses. So I'm going to multiply by final temperature of aluminum and initial temperature of aluminum, because again, what we're trying to do is isolate both final temperatures on one side of the equation. So expanding this expression now will give me mass of H2O times the specific heat of water, getting a little sloppy there, divided by the mass of aluminum times the specific heat of aluminum times final temperature of water. Now, notice, I'm going to multiply this expression times -1 times the initial temperature of water. This negative with this negative will combine to make a positive. So I'm going to write plus mass of H2O, specific heat of H2O, over mass of aluminum, specific heat of aluminum, times initial temperature of water. And this is equal to my final temperature of aluminum minus my initial temperature of aluminum. Okay, here we go. Again, keeping our eyes on the prize. We want both our final temperatures on the same side of this reaction. What I'm going to do, you'll notice, is here we have a negative sign. So to get rid of this expression, I need to add mass of water times the specific heat of water over the mass of aluminum times the specific heat of aluminum times final temperature of H2O. I need to add this to both sides of the equation. All right, I'm going to add that to both sides of the equation. In addition, if I want this, if I want my two final temperatures alone, I need to get rid of my initial temperature of aluminum. So I will also subtract my initial temperature of aluminum from both sides of this equation. Now I'm going to add these two together, and I'm not going to try to squeeze this onto this slide. We're going to bump over to the next slide. Before we do, though, before we bump over, let's just make a note that... Oh, wait. Oh, I just caught a mistake, which is good. This is a negative initial temperature of aluminum. So to get rid of that, I need to add this to both sides. All right. Now, let's look at this. These two cancel each other out. And these two cancel each other out. So on our next slide, our equation simplifies to this. We have, oops, oh, hang on. Here we go. Okay, so we have the mass of water times the specific heat of water over the mass of aluminum times the specific heat of aluminum times the initial temperature of water plus the initial temperature of aluminum is equal to the final temperature of aluminum plus the mass of water times the specific heat of water over the mass of aluminum times the specific heat of aluminum times the final temperature of water. Okay. We are almost there. It feels like we are undergoing near Herculean efforts, but we have finally isolated both of our final temperatures on one side of the equation. Well, we almost have it isolated. We have this pesky coefficient hanging out in front of the final temperature for water. So to get rid of this, we are going to factor this expression. So our right side of the equation is equal to 1 plus mass of water, specific heat of water, over mass of aluminum, specific heat of aluminum, times our final temperature. And again, this is still equal to the mass of H2O times the specific heat of H2O over the mass of aluminum times the specific heat of aluminum times our initial temperature of water plus our initial temperature of aluminum. Now, to solve this problem, we need to divide both sides by this gargantuan factor. But at this moment in time, I think it would actually be easier for us if we decided to plug some values in. I actually think it's going to be easier to get to a final answer if we do that. So let's go ahead, plug in our values for everything we know, which is everything other than the final temperature, and then we will solve. We'll solve out the other end. All right. So let's plug in our values. We have, oh, sorry, hang on. Question. Is this recording going to be in your channel? Yes, it will. You can come back to this recording and view it at any time if you have to bounce early. Or if you're not able to attend live at all. Okay, so let's plug in our values. Our mass of water here is 105.6 0.3 grams. Specific heat of water, 4.184 joules per gram degrees C, over our mass of aluminum, which was 32.5 grams, times the specific heat of aluminum, 0.903 joules per gram degree Celsius. This gets multiplied by our initial temperature of water, which is 15.4 degrees C, plus our initial temperature of aluminum, which is 45.8 degrees Celsius. This is equal to, open parentheses, 1 plus our mass of water again, 105.3 grams, times our specific heat of water, 4.184. Whoa. 4, there we go, joule per gram degree C, over our mass of aluminum, 32.5, 9.0 joules per gram degree Celsius. All of this multiplied by our final temperature. All right, so now it's time to crunch some numbers. So we have 105. First, let's deal with that. 105.3 times 4.184 divided by 32.5 divided by 0.903. All right, so I'm gonna double check this number real quick. 105.3 times 4.184 divided by 32.5 divided by 0.903. So the number that I'm getting here for this expression is, oops, I want that in black, 15.0587. This number keeps going, but we don't have to, because when you look at the significant figure situation, we're limited to 3. 1, 2, 3, 1, 2, 3. So 1, 2, 3. I'm going to wait to round. Whoa. But I'm going to keep track of how many significant digits this number has. Another thing you'll notice here is that grams cancel grams, joules cancel joules, our second mass unit cancels, and degree C cancels degree C. So this quantity is what's the word I'm looking for? Unitless. All right, but it's multiplied by 15.4 degrees Celsius plus 45.8 degrees C. And this is equal to 1 plus, now here, the nice thing is we've already crunched the numbers for what this value, what this quantity equals. It is equal to 15.0587. Hang on one sec. 1 second. All right. So, and again, just like before, we had 3 sig figs. So this number is limited to 3 significant digits, all multiplied by our final volume. All right, so a couple of questions. One, Vraj is asking, wouldn't it be T2H2O on the right side? Again, it's actually the final temperature for water and aluminum, because they're both the same quantity. So that's why I simplified to just writing final temperature as T2, because water and aluminum have the same final temperature in the context of this problem. Sarah, I see your question. I'm going to wait to answer it till the end of this problem, because it's about the exam. Okay, so now where are we? So let's bump to the next slide. All right, so next we are going to multiply our 15.0587 times 15.4 degrees Celsius. That gives us 231.904 degrees C. And again, because the two numbers we multiplied to get this value have 3 significant digits, we can only keep 3. But again, I'm waiting to round till the end. Now we add 45.8 degrees Celsius. And this is equal to, now here's something we can do. Well, here, I'll rewrite it. 1 plus 15.0587 times our final temperature. All right, now when we go to add these two numbers on the right, 15.0587 and this number 1, I just want to make a comment here. This number 1 came from factoring an algebraic expression. So it is exact. It is not measured. It's not going to limit our significant figures. And I just wanted to explicitly state that before I perform the next step. Now, we have here 231.904 plus 45.8 gives us a value on the left side of this equation of 277.704 degrees Celsius. As always, we have to ask ourselves, what is the significant digit situation? Now, the last significant digit in 231 is in the ones place. The last significant digit in 45.8 is in the tenths place. So our answer's last significant digit must reflect the less precise. So the last significant digit of this sum is in the ones place. Now this is equal to 16.0587 times T2. Again, 3 sig figs here. All right, for the final step of this process, we need to finally isolate our final temperature. So we're going to divide both sides by 16.0587. Seven. 3 sig figs in the denominator, 3 in the numerator. So we get 277.704 divided by 16.0587. And that gives us a final temperature of, 17.2930. That is the correct value, but we can only keep 3 of our significant digits, which means our 9 is going to round that 2 up to a 3, making our final answer 17.3 with units degrees Celsius. This is our final answer. All right, so that is the answer to this problem. Hopefully you're able to follow. It is definitely a long problem due to all the algebra, but I will add, in case you're wondering, I will add that this problem is totally exam caliber. So if you're wondering, could we see something like this in an exam setting, you totally could. All right. Speaking of the exam, Sarah has a question on the test. Sarah, I will answer your question, but first, before I do, I'd like to get through the. We've got 2 more questions that people emailed in, and then after I'm done working problems, I'll switch to kind of talking about the test a little bit, or to answer your question. But I'd like to stay kind of on track, on the problem-solving track at this moment in time. So we'll get there. I don't want you to think I'm ignoring you. Okay, so that was our first question. Second question is a really interesting problem. I like this one a lot. So we're told, yeah. Oh my gosh, sorry. Raj just dropped a dabbing emoji that I've never seen before, and it's amazing, actually. Is that an Android thing, or is that an iOS? Is all I'm wondering now. I'll have to investigate that later. Worst case scenario, I will totally copy and paste the dab out of the comment section so I can drop it on my phone from here on out. All right, next question. We're told that sweat... Okay, this one's a weird one. Sweat cools the body because evaporation is an endothermic process. And we're told here that evaporation, the process by which water changes phases, goes from a liquid to a gas, we're told that this has a delta H. Okay, sorry. YouTube has dabbing emojis. Dang, they are up in their game on the mobile scene. It looks like a yellow version of the Odd Ones Out. See, I'm relevant. I know one YouTuber's name. And I can't even take credit for that. I thank my kids for that one. Okay, so we're told that the change in enthalpy for the phase transition for water is a positive 44.01 kilojoules per mole. All right. And then we're asked to estimate the mass of water. Raj is asking, what question is this? This is the next question that I was emailed. I'm taking these in terms of sequential submission. So we're told that the phase transition for water has a delta H of 44.01 kilojoules per mole. And we're asked to estimate the amount of water, estimate the amount of water it would take to cool the body by 0.5 degree Celsius. And we are told to assume that the body has, so we're told to assume a body has a mass of 95 kilograms and a specific heat capacity of 4.0 joules per gram degree C. All right. Now, This is an interesting problem. There's a couple things that may make you feel uncomfortable. The first of which is probably this word estimate. All right. And the only reason why estimate, that word, is here in this problem is because of this word assume. So we're making a couple assumptions. We're assuming the size, or the mass of the body is 95 kilograms. And we're assuming that the specific heat capacity of the body is around 4.0 joules per gram degree C, which is about the specific heat capacity of water. All right. Now, notice, okay? So this, I love this problem because we haven't done anything like this in class to this point, which means this is a great way to test your preparedness for the exam, right? This is a problem we've never seen before, but can we use problem solving to solve this? So first, what are we trying to find here? That is the first and most important question you can ask. And you'll notice that we're being asked to find the amount of water, all right? We are after grams of H2O, all right? Now let's look at what we're given. All right, we're given several things. We're given some information about the body. Whoa. We're told the body is 95 kilograms. We're told its specific heat capacity. So we're given its mass, the mass of the body. We're given the specific heat capacity of the body, 4.0 joules per gram degree C. And then you'll notice that we're asked to estimate the amount of water it would take to cool the body, 0.5. All right? Oops, excuse me. To cool the body by 0.5 degrees. All right? Now, that is a change in temperature. This is a change in temperature. And you'll notice that it says cool, it's getting colder. So that means this is a negative change in temperature. This is negative 0.050 degrees C. All right? So this is looking a little odd because we know the mass of the body, specific heat capacity of the body, temperature of the body. We have enough to calculate Q for the body, the amount of energy that the body is losing. But what are we being asked about here? We're being asked to find water. That tells me we're asked to find the mass of water, right? This is the mass of H2O. So hang on. Sorry about that. One of the downsides to hang on. Here, hang on 1 second. One of the downsides to live casting from home is you're not immune to your kids getting in a fight and needing someone to break it up. So give me like 3 minutes. I will be right back. Okay, sorry about that. I am back. Okay. So where were we? Okay, right. We have enough to find the heat lost by the body, but we're being asked to find the mass of H2O. All right? The mass of water. And you'll notice that we're not given anything about any information about the calorimetry of water. We're not given, we're asked to find the mass, but we're not given specific heat capacity, and we're also not given a change in temperature. So we're going to need to use something else. Now, what we are given is we're told that we're dealing with a phase transition where water goes from being a liquid to being a gas. And we're given, you'll notice, the change in enthalpy for this process. That means that this process is endothermic because we're dealing with a positive, and that it takes 44.01 kilojoules of energy to take 1 mole of water to 1 mole of liquid water to 1 mole of water vapor. All right, now check this out. How do we connect these two? Well, we're aware that we have enough information to calculate how much energy the body is losing, right? That tells us this will be the same quantity as the amount of energy that water is gaining, right? The amount of energy that one thing loses, the other thing gains. To put these equal to each other, we need to multiply one side of this reaction by a -1. This will allow us to calculate the joules of energy being absorbed by water, and then we can use that energy quantity and this in this chemical equation to stoichiometrically solve for the moles and then the grams of H2O. So we're going to use our equation Q equals MCAT to find the energy that water absorbs from the human body, and then use this balanced chemical equation to do stoichiometry with that energetic quantity to find the grams. All right. So first off, let's find how much energy is being released by the body. Oops. All right. So first, we have Q for our body is equal to mass times specific heat capacity times delta T. All right, Q, all right, is equal to, so our mass of the body, we're told to assume that the mass is 95 kilograms, but you'll notice that the specific heat capacity is in joules per gram degree C. So we actually need to convert our 95 kilograms to grams. Now 1 kilogram is 1,000 grams. So these two cancel. So this is 95,000 grams. That's the mass of the body. Times 4.0 joules per gram degree C. Times our change in temperature, which is negative 0.50 degrees Celsius. The units that cancel are grams and degrees C, leaving only joules. So the energy released by the body. Here, hang on 1 second. All right, sorry, still mediating brother and sister conflict. Okay, so we're ready to crunch our numbers. So 95,000 times 4 times negative 0.50 is negative 190,000 joules. All right, now sig figs wise, you'll notice that every number in this expression has two significant digits, and our answer is two significant digits, so we do not need to round. This is the temperature, not the temperature, the energy released by the body. We know that the energy absorbed by water is equal to -1 times the energy released by the body. So the energy absorbed by H2O is equal to a positive 190,000 joules. Now, I'm about to bounce to the next slide. However, before I do, we're going to need to convert joules to kilojoules. If you look at the delta H of a reaction that we're given, it's in kilojoules per mole. So we need to do a unit conversion before we go any further. And I'm going to do that here while I still have ample space. So joules cancel. Our Q of H2O is then equal to 190 kilojoules. All right, now we have the amount of energy that water absorbs in this process. We're ready to take it and do some stoichiometry, because we know that 44.01 kilojoules of energy is enough to convert 1 mole of liquid water to 1 mole of water vapor. And we just determined in the previous step, on the previous slide, that water absorbs 190 kilojoules of energy. So to convert this from kilojoules of water to grams of water, we need to put kilojoules in the denominator. And actually, we can't go straight to grams. We have to first go to moles, because our balanced chemical equation tells us that 1 mole of water is vaporized by 44.01 kilojoules of energy. kilojoules cancel. All right, 190 divided by 44.01 equals 4. Oh, well, here, actually. We're not ready to crunch our numbers yet, right? We were asked in this problem to determine the amount of water in grams. So we actually have one more step. We need to convert from moles of water to grams of water. Now here we need to calculate a molecular weight. Hydrogen has an atomic mass of 1.008 AMU, oxygen 16.00 AMU, and in one molecule of water we have 2 hydrogen atoms. This gives water an atomic mass of 18.016 AMU. Now, given the numbers that I use here for significant digits, we would have to round to the hundredths place. So 18.2 grams of water in 1 mole. Now we're ready to crunch our numbers. All right. So, does the 95, yes, affect the sig figs? Yeah, you'll notice every number in this problem has 2 sig figs. So that is going to limit our answer in the end. So here we have 190 divided by 44.01 times 18.02 comes out to be, well, our value 77.795. All right, sig figs wise, we're only allowed to keep 2. So our final answer will be 78 grams of water. It takes approximately 78 grams of water to cool the body by 0.5 degree Celsius. All right, and that is the correct value, units, and sig figs. All right, for our third and final question, actually we only got 3 this time around. This problem comes from the ACS study guide. So here we're told that we're given a balanced chemical equation between fluorine, elemental fluorine, and sulfur, and we're told that this produces sulfur hexafluoride. All right. And then in the problem, we're told that we have a mixture of, we're told that 9 moles of F2 are mixed with 9 moles of F2 and 4 moles of sulfur are allowed to react. And then the question is, how many moles of fluorine remain after, let's see, where do we, it says 3 moles of sulfur have reacted. All right. How many moles of fluorine remain after 3 moles of sulfur reacted? Now, here in this type of problem, anytime you see this word remain, you're going to have to take this a little bit conceptually. Oh, sorry, I'm getting a question. Raj, you're saying, I sent you an email in Canvas. Did you not get it? I haven't yet, but once I finish working this problem, I'll check it real quick. So maybe we get not just one more, but two more questions in this office hour. So first, whenever you see remain, you've got to set up just a conceptual thing. You have your initial quantity of grams, moles, what have you. You have the amount that reacted, or the amount that reacts. And if you subtract the amount that reacts from the initial, what you're left with is what remains. So if we're after how many moles of fluorine remain, we have to take the initial, which is 9 moles of F2. We need to subtract how much reacts, and then we'll be able to calculate how much remains. Now, the amount that reacts to determine that quantity, we're going to have to do some stoichiometry. So we're asked how many moles remain after 3 moles of sulfur have reacted. So first, we need to take our 3 moles of sulfur and determine how much fluorine 3 moles of sulfur will react with. To do that, we're going to put moles of sulfur in the denominator and moles of fluorine in the numerator. And from our balanced chemical equation, we see that 1 mole of sulfur reacts with 3 moles of fluorine. Moles of sulfur cancel. This equals 3 times 3 is 9 moles of fluorine react. All right. This is the amount that react. So we start with 9 moles. We react 9 moles. And then when we take the difference, we see that 0 moles of fluorine remain. So in this problem, 0. Oh, I'm seeing I forgot. It should be an F2, F2, F2. All right, so the answer to this problem is 0 moles remain. Now, again, the way you find how the quantity that reacts is you look at your other reactant. In this case, we're told that 3 moles of sulfur have reacted, and we use stoichiometry to determine that 9 moles of fluorine would react with 3 moles of sulfur, and then we do the subtraction. Okay, so hang on, I'm going to check my Canvas real quick. The word on the street is that we have one more problem waiting there. Oh, yep, look at that. I have a message in my inbox. Okay. Page 271, question 6. So my first question is, what edition of the texts are you using? So you told me page 271, question 6, but I don't know if you're in the first or second editions here. And then second, if in the future, if you could send me with your question a picture of the actual problem. So when you submit questions in the future, send a picture of the actual problem, because what I have to do right now is dial up the a digital copy of the second edition to find this problem. So let's see, mastering. So my apologies to everyone watching this video. This may take just a little bit of time. Ba-da-boom. Oh, yeah, no. Totally no worries, dude. Nope. Sorry. This login's making me add my country, and I typed USA, and they told me it was not a country. I don't know if that's resentment or what. Oh, now we're doing two-step verification. Hang on, we'll get there. Okay. It's never done this to me before. I guess they want proof I'm not a robot. All right. Thank you, Pearson, which is the publishing company that manages this website. All right. Oh, wait. You said... Oh, second edition. Hang on. Actually... dialed up the third. Right. Now we're going to go to these. Okay. All right. Okay, so it's loading. Quick question from exercise 7, which is gas laws. Are you taking this? Oh, so Sarah's asking a question whether or not I take questions from the exercises or just lecture material. I will totally take questions from the lab exercises. Sarah, if you want to message me either an email or on Canvas a picture of the exercise, because I don't have that right at this moment, I will do that problem right after I'm done doing this question that Raj asked me. I will totally hit that up. Just shoot me a picture of the exercise question in particular. All right, let's see. Raj, you said yours was on page 271. Okay. This is 243. Page 271. Question 76. Okay. Alrighty. Okay, so let's see. Question 76. So consider the generic reaction. Actually, I'm going to move this over. Oops. Alright, consider the generic reaction A plus 2B going to C plus 3D, and it has a delta H of 155 kilojoules. All right, determine the value of delta H for each related reaction. Okay. So here, let's open a new slide. All right, let's open up a new slide. So in this problem, this is let's see. So this is chapter 6 from the textbook, problem 76. Chapter 6, problem 76, and we are told that the reaction A plus 2B, which produces C plus 3D, we're told this has a delta H of 155 kilojoules. Now, just so you know, the book will often list changes in enthalpy in terms of kilojoules, but it's always kilojoules per mole reaction. All right, so it gives us this, and then it asks us, there's 3 parts, A, B, C, to determine the value of delta H for each related reaction. All right, so the first one, where am I? Okay, they want to know what is the delta H for this reaction. 3A plus 6B producing 3C plus 9D. And in order to solve these, we have to compare the delta H, the reaction that we began with to the reaction that we're given. And one thing that you'll notice is we have a common factor here of 3. Everything in this new chemical equation has been multiplied by 3 when you compare it to the previous chemical equation, which means that our change in enthalpy will be equal to the change in enthalpy for the original reaction multiplied by that same quantity. So this will be 155 times 3. All right, so our delta H then for this expression will be 465 kilojoules per mole. All right. Let's look at part B. You'll notice here, so we've got C plus 3D producing A plus 2B. And here, you'll notice that the reactants in this equation are the products of our given equation, and the products of our equation here are the reactants in our given equation. Whenever you switch back and forth, whenever you switch your products and reactants, your new delta H is going to be equal to your old delta H. It'll have the same absolute value, but the opposite sign. So you have to multiply the old delta H by 1. All right, and then finally, part C. Part C, we're given an equation that has, let's see, where are we? Okay, this is 1/2 C plus 3/2 D producing 1/2 A plus B. All right, so the first thing that jumps out at me is here we have C and D, again, swapped with A and B. So we have switched our reactants and our products. So the delta H for our new reaction is equal to 155 kilojoules per mole, which that's the delta H of the old reaction. Same quantity, but then we have to multiply this thing by -1. All right, but then the second thing is the stoichiometric coefficients have changed. You'll notice here we have 1/2 C, 3/2 D, 1/2 A, and then 1 B. And when you compare these new stoichiometric coefficients to the ones we started with, everything in the first reaction has been multiplied by the same number, and that number is 1/2. So we've already flipped it, so we changed the sign for delta H, but now we have to multiply our delta H by 1/2 because we multiplied A, B, C, and D each by 1/2. So our new delta H is going to be negative 155 divided by 2. So this will be a negative 77.5 kilojoules per mole. Alrighty. Okay, cool. Raj, I'm glad I was able to help. Okay, Sarah, I emailed you a picture problem. 16 at the top. Okay, let me take a look. Sweet. Boop. All right, hang. All right, just give me a second. It's saying that the Sarah, see your email. It's not loading on my phone, so I'm gonna try. Logging in on my desktop. Look. So we'll see what's faster. The phone. Or the desktop. All right, let's take a look. Alrighty. Desktop was the way to go. Oh, wait, that's not. Okay. Okay, sweet. Finally, we can get this into a better orientation. All right, thanks for bearing with me, everybody who was bearing with me. If you're watching this live, I've got. Okay, yeah, no, I totally got it. Okay, Sarah, exercise 7. Okay, let's see. Question 16. Okay. Awesome. So Dalton's law of partial pressures. Okay. So this is just for everybody at home. This is from lab exercise number 7. It is problem 16. All right. So we're given Dalton's law of partial pressures. And then we say if a sample of oxygen gas is collected over water at a pressure of 9.2 atmospheres and 25 degrees Celsius, what is the partial pressure of the oxygen gas? Okay. So we're told that O2, now this is clutch. This phrase is collected over water. You will see this over and over and over again. Really good exam candidate type of problem. O2 is collected over water at a pressure of 0.921 atmospheres and 23 degrees Celsius. And we're asked to find the partial pressure of water. Okay, first we got to lay down a couple conceptual things. So first, this thing collected over water. This is very common. There are many types of reactions that produce gas over water, where gas bubbles out of the aqueous phase. You've probably even seen some of them in lab this semester. All right. Now, here's the thing. I'm going to use a little visual aid. Whenever a gas is collected over water, so let's say we're doing a reaction that starts forming little bubbles. All right, and we're producing gas. That gas is always going to be a mixture, because whenever you have liquid water, you have liquid water evaporating into water vapor slowly. So whenever you see, I'm sorry, I forgot that. Whenever you see the phrase is collected over water, that is code. Here we go. Whenever you see the phrase is collected over water, that is code for is a mixture of O2 and H2O. Now, sorry, I should say, it's not always going to be a mixture of oxygen and water. It'll be a mixture of whatever gas is being produced in water. So whenever you see a gas is collected over water, that means a gas is collected as a mixture of that gas and water vapor. All right. That means that this pressure, it's not the pressure of oxygen, it's not the pressure of water, it is the total pressure. And Dalton's law of partial pressures tells us that the total pressure is equal to the partial pressure of every member of that mixture. So since this O2 is collected over water, since this is a mixture of oxygen gas and water vapor, the total pressure here is a mixture of oxygen gas, the partial pressure of oxygen gas, and the partial pressure of water. Now, we've already been told that we're trying to find the partial pressure of water. We know the total pressure because we're given the total pressure. That means we need the partial pressure of water, and that is where our temperature comes in. All right, this 23 degrees Celsius. Now, turns out that the vapor pressure of water, is varies with temperature. All right. So, whenever you are collecting gas over water, to determine the vapor pressure, the partial pressure of water, you need to know the temperature, and here, that's why they give it to us. They tell us that this happens at 23 degrees Celsius, and so you need to look up a table that gives the vapor pressures of water as a function of temperature. Oh, let's see. Here we go. So I am currently, I dialed up wiredchemist.com, which has a great vapor pressure table, and it is telling me, because I don't have this number memorized, that the partial pressure of water at 23 degrees Celsius is equal to 21.1 torr. All right? 21.1 torr. Now, we're going to have to do a unit conversion. We're going to need to do a unit conversion because our vapor pressure of water is in torr, but our total pressure is in atmospheres. So to find the partial pressure of water, we need to convert one or the other. I'm going to convert torr to atmospheres. The conversion here is 760. Torr is 1 atmosphere. This unit conversion is exact. So we get 21.1 divided by 760 is 0.0278 atmospheres. All right, now that we know the partial pressure of water in atmospheres, we can solve for the partial pressure of oxygen. We do so by subtracting the partial pressure of water from both sides of this equation. This gives us total pressure minus partial pressure of H2O is equal to the partial pressure of O2. So that's 0.921 atmospheres minus 0.0278 0.921 minus 0.0278. So our value here is 0.8932 ATM. Sig figs wise, our least precise number has 3 decimal places, so we need to round. So the partial pressure of O2 will be 0.893 atmospheres. And that is our final answer. Value, units, and sig figs. So the take home here is anytime you're dealing with something being collected over water, you need to include the partial pressure of water vapor in your calculation. And that value, I don't require you to memorize that for any partial pressures of water for lecture exams. I'll provide those for you. But they often don't give it to you when you're working in the homework, or when you're doing lab exercises, they expect you to look them up. So anytime you see that over water, bust out the table at the back of chapter 5 and look up the vapor pressure of water at whatever temperature we're doing in the problem. All right, cool. Okay, so that is the last problem for this office hour. Hopefully, it was helpful. I do need to run. We've been rolling an hour and a half, and my baby's waking up from his nap. But before we do, Sarah had a question about the test. Okay, so she read that I'm making the exam half take-home, half multiple choice. Will each of these portions be worth 50%, or is the multiple choice worth less? Okay, that's a great question. Is it going to be 50-50 equally weighted, or is the multiple choice going to be less? I don't know for certain yet. I'm still in the process of writing problems to fit in the writing problems for the multiple choice bank. So I'm building this from scratch for the first time this semester. It partially depends upon, because I'm in a little bit of a time crunch to get it up and running. It depends upon how much I'm able to flesh out and how satisfied I am with the multiple choice selection for exam 2. So it's possible that they'll be weighted equally, or maybe one will be weighted more, one will be weighted less. I'm not exactly sure at this moment in time, but what I can tell you is as we get closer to the exam date, I will have a better idea for what size I'm going to make each, and I will let you know explicitly a couple things. So exam 2, here's what I can tell you right now. Exam 2 will have 2 segments. There will be an online portion on Canvas, which will be multiple choice. And then there will be a second portion that will be written take home. Canvas multiple choice written take home. I can tell you right now that the Canvas portion will be timed. I don't know the exact amount of time right now because it depends upon, again, how long it'll be. So once you start, you'll have a limited amount of time to complete it. For the written take home, you will have 24 hours to complete. To complete it and email me a scanned copy. So for the exam, I will not be accepting phone photos, I think. We'll see. It's got to be high quality. It's got to be legible enough to grade, because if I can't grade it, then I can't give you points, and then you're going to get nothing. Something to keep in mind is no late submissions will be accepted. So you'll have 24 hours to complete an email in a scanned copy. It does not matter if you're 1 minute late. If it's a late submission, it will not be graded. Just so that we're fair to everyone. That's kind of like the pencils down moment. So that's as much as I know right now. Again, I don't know the extent of the time that the multiple choice will receive, part of it depends upon how long I make it problem-wise. Definitely sometime under an hour is what I'm shooting for, but the specific time depends upon how long it comes out. Yeah. Like Sarah just asked, can we use a scanner app on a phone? Totally. I realized, I said when I wrote scanned copies, I just realized that not everybody has access to that. Thing is, most phones have pretty decent cameras, so as long as it's legible, I'll accept it. When I say legible, I mean readable. If it's super pixelated and I can't read it, then then I can't. But anyways, so that's what I know at this point. Thanks everybody who joined in. I was going to say mostly Vraj and Sarah, but I just scrolled back through the comments, and it's only been Vraj and Sarah. I've seen some views fluctuating. We've fluctuated between 3 and 4, so we've got a couple lurkers out there. Which is nothing wrong with lurking. It's my favorite thing to do. Anyways, hopefully this was helpful and will continue to be helpful. Again, this will remain up online. I'm a little bit behind uploading slides. I haven't done Wednesday's lecture yet, but I will be uploading those soon, as well as these slides will get uploaded to Canvas as well. Thank you everyone for sending in questions. Some questions were sent in by people who weren't able to watch live, but they'll be there for you to watch later. And again, please, as always, I want to know what's good. I want to know what's bad. What's good about this format? What's bad about this format? And super critical for me is how can I help you? How can I help support you in this time? Because it's a weird time to be in college. Weird semester to be in college. Anyways, hopefully you found some benefit from it, will find some benefit from it. And I hope you all have a good weekend. We will be back broadcasting on Monday, so I look forward to seeing you all then.